Welcome to Chapter 2. In this chapter we discuss programming the msp430 in C using Code Composer Studio. We begin by taking a quick look at TI's support ecosystem. Starting in the upper right hand corner, we see that TI provides a rich set of development tools. In this course, we'll spend much of our time working with Code Composer Studio and the Launchpad target board. But there are a great many more tools, such as the various optimizers and advisors. To name just a few, the Optimizing C compiler, the Grace driver library, GUI, and the ULP advisor, that is, ultra low power advisor. In the upper left hand corner, we have runtime software. This bubble includes code that you can use to build your own programs. Best of all, these libraries ship with their source code, and free of charge for TI CPUs. We'll examine more about these on the next slide. Lastly, the lower item highlights the rich community of support for TI's products through the forums, EDE pages, wikis, in-person and online training. In fact, that's probably where you found this training. TI provides a layered approach to software. We've taken this approach for two reasons. One, we realize different people approach their work in different ways. Some like to work at a very abstract level, while others don't. And two, you may want to mix and match which layer you're using. For example, even if you prefer working at the most abstract, that is easy to use layer, at times you might need to use a lower layer to access some uncommon feature or something specific about the hardware. In any case, each layer is built up upon the lower ones, and they can all work together at the same time. Let's quickly review the layers. Starting at the bottom, we see the msp430 microcontroller that we discussed in Chapter 1. The next layer up, that's the one we called the low-level C header files, includes a set of header and linker files. These files provide symbolic definitions for all of your devices, registers, and their bit fields. In fact, TI creates a unique set of header and linker files for each specific msp430 device. Using these, you shouldn't ever have to memorize a bit field definition again. Even better, they provide a common register level vocabulary that is common amongst msp430 programmers everywhere. We will look at the details of these files later in the chapter. The next layer is called TI Wares, as this layer is available for many different TI processors. In our case, the actual product is called msp430ware. The driver library, or driverlib, we sometimes call it, is one of the main components of msp430ware. We'll be examining and playing with driver library throughout this course. We'll jump into this starting in the next chapter. Finally, at the top of the slide we see Energia. Energia is the name for the Arduino port that runs on TI processors. It's the most abstract library and is the easiest to use. Actually, if you're familiar with working with Arduino, you probably already know that it's really just a C library that runs with C and C++ framework. In any case, we'll explore all the fun of Energia and Arduino in a later chapter. Next, let's briefly review some of the development tools that are available for the msp430. The msp430 is supported by a vast set of development tools. Here we examine four options. First, the msp430 is well supported by IAR systems. IAR is the benchmark in the industry. In fact, their compiler is the most efficient option available today. Even though it's a more expensive option than the others, it's a very popular one. If you want to try them out, IAR provides a free option that is time or code size limited. TI's Code Composer Studio, or CCS for short, is another full-featured development suite. Like IAR, TI provides a full function evaluation of their tool set. Starting with CCS version 6, though, TI now includes the new GNU GCC compiler. When selecting this compiler option, rather than the TI compiler, you can use CCS for free and without code size limitations. Even if you choose to purchase the full version so that you can gain access to TI's Optimizing C compiler with an unlimited code size, you still don't have to spend much money for the product. We'll explore CCS in much more detail in the rest of this chapter and in the upcoming lab exercises. Energia, the Arduino port for the msp430, provides another free tool set for you to choose from. It's a community-based project utilizing the GCC compiler. The Energia IDE provides the same look and feel as you would find with Arduino. The big limitation of Energia's and Arduino's IDE is that they don't provide the ability to single step through your code or set breakpoints. But starting with CCS version 6, we now solve that problem by letting you import and debug Energia sketches. That's a big plus if you want to take Energia, that is Arduino, to the next level. Finally, we show the open source column. You can use the GNU tools as well as msp430 debug from the command line or call them from gmake. Next, we quickly review some of the web-based community and support options. I'm a big fan of TI's Processors Wiki. Just go to processors.wiki.ti.com for a wealth of information on all of TI's processors and microcontrollers. In fact, we've highlighted 2 of the items on the screen capture of the wiki site. First, being you're in the msp430 class, you might find the msp430 section of the wiki interesting. Also, if you scroll towards the bottom of the wiki page, you'll find the training homepage. Clicking that link takes you to the hands-on training for TI embedded processors. You can see that at the top of this slide. This page features many of the courses developed by TI's Technical Training Organization, also known as the TTO. Clicking the link for the msp430 training then takes you to the workshop's homepage. Again, this is likely where you found these course materials that you're going through right now. We conclude the support topic by glancing at the E2E forums. Here's a place where you can get answers to your processor, tools, and software questions. In fact, while TI applications folks staff the various forums, answering questions and providing support, you'll find that the msp430 community at large provides a great many answers and opinions. Our msp430 users are just as knowledgeable and passionate about this wonderful CPU as we are. The final item in our ecosystem discussion addresses a question which we often get from students. Where can I go for more information? This list is by no means exhaustive, but these are 2 highly recommended texts. I've read a good portion of the first book by John Davies and found it an excellent way to learn more about the msp430. The book is a couple of years old now, so it doesn't discuss TI's latest devices, but the information is so darn good. To tell the truth, the basic lessons don't vary much anyway. But here's to hoping that one day John will come out with an updated edition. A colleague of mine recommended the second book we've shown here. I haven't had the opportunity to review that one yet, but I'm hoping to one of these days. In any case, here are 2 good options for you to take your msp430 knowledge to another level. Next, let's turn to examining Code Composer Studio itself. First, let's start off with the question, CCS is an IDE. What does IDE mean? Okay, officially IDE stands for Integrated Development Environment. But personally, I like the definition Integrated Debugger and Editor, because that's what it really ends up being. We can edit and build our code in the same tool that we use to debug our code. CCS is actually based on the open source Eclipse framework. There's a large consortium of companies that make and contribute to Eclipse. So if you've already used an Eclipse-based tool before, you've probably already got a good handle on Code Composer Studio. In either case, you'll get a chance to learn more about Eclipse as well as some of the TI CCS extensions in this chapter. We begin the functional overview with a quick look at the flow of code from the text editor to the debugger. As we can see in the diagram, we can write our source code in C, C++, or assembly, though C is by far and away the most common way to do it. When we hit the build button in CCS, the compiler creates assembly code, which is then turned into object code by the assembler, and finally, the linker stitches together all of our object code into a single executable program. Besides stitching code together, what else does the linker do? If you said allocate memory, then you're absolutely correct. As the linker combines our object files, as well as any libraries that we've included, into our executable output file, it assigns memory addresses to all the symbols that we defined in our program. That's one of the beautiful features of C. We can represent various elements like variables using symbols, and we don't really need to worry about things like specific addresses. Later on, the linker handles that chore for us then. In order to assign the right addresses, though, you need to supply a linker command file to the linker. In this case, we show it as user.cmd, Thankfully, though, TI provides one of these for us whenever we create a new project inside of CCS. Later on, in the chapter on non-volatile memory, we'll dig into the linker command file with a bit more detail. One last comment on this slide is the .map file. This is a report created by the linker which tells you which addresses it assigned to everything in your program. Among other uses, this is where we can find the size of our program. Before we look more closely at the debugging side of this diagram, we want to show you one more edit side feature. If you choose to use TI's real-time operating system, also known as TI-RTOS, there are a couple of additional items you'll use. Fundamentally, TI-RTOS is just a code library that provides a number of operating system functions. In this diagram, that's represented by the TI-RTOS libraries box that would get pulled in by the linker. Another big part of TI-RTOS is the graphical configuration tool that it comes with. This GUI makes it easy to create RTOS data objects that you need for your system, as well as selecting those parts of TI-RTOS that you want to use. That's because TI-RTOS is very scalable. You only need to include the parts in your final program, just those parts that you're interested in using. If you don't like to use GUI tools, you don't have to. The GUI just creates a JavaScript file, which in turn creates a number of source files and an additional linker command file. You can actually just create that JavaScript file on your own if you want. Finally, let's go ahead and look at the debug side of the CCS Functional Overview. The CCS debugger provides us with the ability to test and validate our code. We'll look at many of its features in the upcoming lab exercises, such as single-stepping code, setting breakpoints, using watch windows, and so on. As we see here, the debugger is just an interface. It provides a convenient way to load and test our programs. What does the debugger connect to? Well, that's up to you. Many TI processors provide a software simulator. Although with inexpensive target boards, such as the msp430 launchpads, most users just prefer running their code on real hardware. TI and many of our third parties provide other possible target boards, EVMs, and so on. CCS can be configured to work with any of them. Which board you want to talk to is defined as the connection, and that information is stored in the target configuration file. Its extension is .ccxml, and if you happen to peek into this file, you'll find that it's actually an XML description of that connection. In most cases, you won't need to concern yourself with the target configuration file. When using the msp430, as long as you specify the connection type when you create a new project, CCS will automatically create the ccxml file for you and add it to your project. Finally, if you want to be able to debug code on your own target board, a board you built, you're going to need to have a link or a connection between the msp430 on that board and your computer. TI provides this connection. We sell something called the msp430 FET. I think that stands for Flash Emulation Tool. But it's a cable and a little pod that lets you connect your computer and the board together. Some of our third parties also create something similar. This is something you can buy if you want to connect your own board up. At some point along in your design, you'll probably need to do that. So we've finished looking at the high-level overview of Code Composer Studio. Let's look at how CCS, and Eclipse programs are organized. As with most IDEs, Eclipse and CCS are organized around projects. You'll create a project for each program or library that you want to develop. The Project Explorer window provides a graphical view of your projects, including all of their associated files, such as, in this example, main.c. Along with projects, Eclipse also defines a term called workspace. A workspace is just the folder that contains your projects. As we'll see in the next slide, your projects can either reside inside the workspace or be linked to the workspace. It's often convenient to think of the workspace as being analogous to this Project Explorer in the CCS GUI. In most cases, whatever exists in the workspace folder shows up in the Project Explorer window. Let's look at the projects and workspaces in a bit more detail. As described on the last slide, projects contain references to all of your program's source files and libraries. In Eclipse, and thus in CCS, files can either reside inside the project directory or be referenced via a link. In fact, whenever you add a file to a project, CCS will ask whether you want to copy it or link to it. It's common to see source files copied into a project, whereas libraries are typically linked. That being said, the msp430 team recommends copying their driver library into your project. I guess it just comes down to a matter of preference. Once again, a workspace is just a folder where you keep track of your projects. Whether the project folders are contained inside the workspace directory itself or found in an external folder that's linked into the workspace, Eclipse uses the workspace folder as a means of organization. Along with keeping track of projects, workspaces also contain workspace level preferences. Setting an Eclipse parameter in the workspace means that it's available to all the projects and you don't have to add it to each project individually. By the way, Eclipse lets you have as many workspaces as you want. A fact that you might have already deduced when starting CCS, since it asks you which workspace do you want to load, or in other words, which workspace do you want to use. In this workshop, we've decided to use just a single workspace. That actually works pretty well for us, and it lets us have all of our lab projects in a single workspace where we can reference between them. What I mean is you can go, oh, what did I do in that last project? You can go open it up and take a look at it. That's what it lets us do, and that's pretty convenient. Some people like to have one workspace per project. On the other hand, some people only ever create one workspace and everything goes in it. You can organize it however you want. One last thing before we move on to the next topic. While we don't really need to concern ourselves with this in this workshop, we recommend that you use caution when linking files into your projects. While it's efficient and often smart to share a link to a resource such as a library, you should give thought to how other team members will be able to build your projects. If you've ever, maybe you've received a project from somebody else and you go to build it and it doesn't work. It usually ends up being because people put files in different places of their file system. You need to solve that problem and make it easier for us to share projects. Eclipse provides a method of doing this called portable projects. That is, using IDE macros, or if you want to think about it, IDE variables might be another way to say it. But using these macros, we can make it easier for others to port our projects into their own file system. We recommend that you go search the TI Wiki for CCS portable projects if you want to learn more about this. To finish up our discussion on CCS, let's quickly look at how to create a project and add files to it. Here's an example of creating a new project in CCS v6. To begin with, we need to select New CCS Project from the File menu. From this point, we just need to fill out the dialog. We can start with which device we're using. When we select a device, CCS automatically includes the correct device-specific header and linker command files. You select the device by using the drop-down menu pointed to by the Select Device arrow shown on the slide. This can be a long list, so you might want to type part of the device name into the target text box. In this example, we typed 5969 and it narrowed down our list of choices. The next item is that we need to specify how our target will be connected to CCS for debugging. In most cases, you're just going to want to choose TI msp430 USB 1. In fact, this is the one we're going to use in our upcoming lab exercises with the launchpads. Third, you'll need to give your project a unique name. Eclipse requires that every project within a workspace has a unique name. Fourth, we need to tell CCS what type of project we're creating. In most cases, you're going to want to create an executable program, but you could also choose to build a library. Fifth, we need to tell CCS where we want our project to be created. By default, CCS will create a folder inside the workspace using the project's name. If desired, you can uncheck the default location, that default location checkbox, and pick another location. In this workshop, we'll create some projects inside the workspace, while others will uncheck this box and put them in a workshop lab folder. We'll give you instructions on how to do that in each of our lab exercises. Finally, CCS provides a number of project templates. These are useful starting points for your programs. Some create simple examples such as Hello World. Others, such as the TI RTOS templates, handle linking in all the required libraries and tools that you need to get these projects to build. Bottom line, if there's a template close to what you need to do, we recommend using it. It's easy to add files to your projects. In fact, there's a couple of different ways you can go about it. Here, we're showing that you can right-click on the project and select Add Files. Then, of course, you need to select the files you're interested in. And finally, CCS will ask you whether you want to copy the files into your project or just link to them. Note, if you select Link Files, you can specify the reference point. As we said earlier, you can make your projects portable by creating a custom reference point, that is, an IDE macro variable, for each directory of files or libraries that you add into your project. If you've already created these references, you can select them with the drop-down shown here. Again, this isn't something we're going to need to do in this workshop. We'll mostly just copy the files. Finally, you can add files to your projects in other ways. You can drag files onto the project using, Project Explorer and Windows Explorer. Or, within Windows Explorer, you could just add the files to the project folder. Whichever method you use, CCS should present you with that copy or link dialog that we show here. Before we jump into the lab exercise and start using CCS, we thought it might be good to cover a few hints when using TI's C compiler. As with most modern C compilers, the TI compiler provides upwards of 100 different build options. In most cases, you'll only need to use or know a few of these. That said, we recommend that you have somebody on your team review the Optimizing C Compiler User's Guide, just in case there's one of these minor features that could be useful for your projects. As we show here in the first option, if you specify which processor you're using, when you're creating a new project, CCS will automatically pick the appropriate processor options for you. All modern msp430 devices provide you with 20-bit addressing. This lets the CPU use more than 64K of memory, should your processor include that much memory. The choice of code and data models will depend upon the amount of memory found on your specific device. Once again, CCS will choose an option for you based upon your target processor. The other two categories shown here have to do with debugging and optimization. Gone are the days where we had to explicitly turn on the debugger. That's just now turned on by default. Though if you want to be able to see how your compiler implemented your C code, you can turn on interlisting of C and assembly code. You may want to use the -SS option to do that. When optimizing your code, though, you may want to remove the -SS option, as this may inhibit the optimizer's capabilities. In this case, you could substitute the -K option in its place. This tells the compiler to keep the generated assembly file, but it just won't interlist it with the C code. If you want to use the optimizer, you do explicitly have to turn it on. This is done with the -O option. You can invoke the optimizer at any one of 5 different levels of aggressiveness. The higher the number, such as -03 and -04, the more aggressive. If code size is important to you, then you'll want to use the -MF option along with the optimizer. MF tells the compiler how concerned you are with code size versus code performance. Finally, CCS makes it easy to switch between debug and optimization, or what they call release, modes. To this end, they automatically include 2 sets of options in any new project you create. These sets of options are called configurations. How can we modify the compiler's build options and configurations? Well, let's turn to the next slide. You can modify the project's build settings and compiler options by opening the project properties. Do this by right-clicking on the project and selecting Properties. As we can see here, there are a number of different pages that are dedicated to various compiler options. One little hint though, when you change build options for one configuration, such as debug or release, it doesn't necessarily affect the other configurations. If you're changing options, you may need to replicate this change for each of the build configurations. Looking at the msp430 data types. Here's a couple of key things to keep in mind when using the msp430. First of all of our current msp430 devices are 16-bit processors, and therefore the ints are 16 bits. Shorts, as you might expect, are also 16 bits. If we go back to the top of this slide, thankfully we can see that the msp430 is a byte addressable processor. Thus, chars, or if you like to call them chars, are 8 bits wide. The advantage to this is that it makes them a lot more memory efficient when we build our programs. Hopefully the remaining data types here are self-explanatory. If you want more information on all the compiler's data types, please refer to the Compiler User's Guide. Before we finish, a quick overview of the device-specific files that we mentioned earlier in this chapter. As we said earlier, TI creates two unique files for each MSP430 device, a header file and a linker command file. As shown here for the MSP430 F5529, we have two similarly named files, one ending in .h, the other ending in .cmd. Let me pose a question for you. Which code generation build tool assigns addresses to the symbols in our C programs? If you said linker, you're correct. Why do I ask this question? It simply goes to understanding the two files we're discussing here. Here's the simple rule. If a hardware symbol represents an address, you'll find its definition in the linker command file. An example of this would be the name of a peripheral register. In the case here, for example, the watchdog control register, WDT-CTL. In this case, the symbolic name for the register actually represents the address of where you'll find it in the memory map. All of the other symbols are defined in the device header file. Two examples of this are found on the slide. The watchdog password and the watchdog hold bit values are specified in the device's header file. We'll see an example of this in the upcoming lab exercise. One more thing while we're talking about the compiler. Modern C compilers often include built-in functions. These are called intrinsic functions. Compilers often include intrinsics to allow you access to hardware-specific features. For example, on the MSP430, it's handy that the compiler gives us easy access to the low power modes and the ability to modify the status register. In the first few lab exercises, we'll make use of the delay cycles intrinsic function. This makes it easy for us to tell the processor to do nothing for a specified period of time. Note though that this is really a bad thing to do in real life. We use this simple cheating method of delaying the code until we introduce interrupts and timers later in the workshop. That's the right way. Using timers and interrupts are the right way to actually delay the processor should you need to do that in your real program. Finally, we've reached the lab exercise. In the lab exercises we've created for this chapter, you'll utilize the two built-in templates for creating one, hello world, and two, blinking an LED. Finally, we'll show you how to put the original code that, the one that came with the Launchpad, back into the non-volatile memory of your MSP430. By non-volatile memory, we mean either the flash or the FRAM, depending on which Launchpad you're using. When you have time, either in class or later at home, you can explore how to load the binary program into the MSP430's memory without even needing an IDE. You can use the MSP430 flasher rather than Code Composer Studio to do this. Remember, this lab is more about the tools than the code. We'll dig into writing code starting in the next chapter. The main goal of this exercise is really just to become familiar with Code Composer Studio.